Hi class, and welcome back. Happy Friday. So today's album recommendation is the exquisite magnum opus, Midnight Organ Fight by Fret and Rabbit. This is... So Fret and Rabbit is a fantastic Scottish band whose lead singer unfortunately passed away a couple years ago, very tragically and publicly. But this album's really one of the best albums, and certainly one of my favorite albums of my life to date. I was fortunate enough to see Fright and Rabbit perform, I think either three or four times before the lead singer passed away, and this is my favorite of their albums. It's highly recommended. It's definitely a breakup album, so it's a bit sad, it's a bit loud and angry, and the lead singer has a fantastic Scottish accent, which is just delightful. So enjoy. Today we are talking about divergence and Green's theorem. So we're going to have next week another theorem called the divergence theorem. And they're not the same, and I just want to make this a note now. So Green's theorem, the divergence form, is not the same as the divergence theorem. And we'll discuss that next week. But just to clarify, we haven't done the divergence theorem yet. We're going to talk about it next week. It just happens that these two different forms both involve divergence, but this one involves divergence in 2 dimensions, and the divergence theorem really involves divergence in 3 dimensions, and so there's a difference there. So we'll come back and visit that. But before we even talk about what divergence is, I want to justify what we're doing. Often in this class, we've seen that there are dual ways to look at the same objects. So, for instance, we said that a line, we could either, right, let's say this is my line L, we could either view this line as being vector valued, so it's parameterized by some point on the line, so if this is A, and let's do, and V goes along the line, let's do this all in colors, then you might get a vector valued form of the line A plus TV. On the other hand, we said that there's an implicit form. So this was the parameterized form. Implicit form for the line, which we arrived at by constructing a normal vector to the line, and then doing this, some formula that looked like n dot x minus a equals 0, where x was now an arbitrary other point on the line, and x minus a is now that vector along the line between a and x. And so the key thing I want to draw out here is the duality is between viewing an object either tangent to the curve or perpendicular to the curve. So this is like the tangent direction, and this is the perpendicular or normal direction. And so in view of that duality, we have a new version of Green's theorem, which is going to fall under this normal column. So, but let's justify that our previous one had to do with the tangent version. So previously what we had was Green's theorem told us that the double integral of r of the scalar curl of a vector field is equal to the flow along that curve, the boundary of r, of the vector field. And our pictures for this looked something like, if this is boundary of r and this region is r, then the flow, we said, was trying to understand at a point P of t here, f at that point might be somewhat agreeing with the tangent direction. So we looked at kind of p prime of the function, and this dot product is comparing, I'm writing too much in red, comparing p prime to f, compares Right, so it's comparing the tangent direction of the curve to the vector field and seeing how much they agree. And that agreement is through the dot product. The orthogonal or normal way of looking at this picture looks a little different. We take the same region, here's a similar looking region, and at a point, so here's my point P of t, what I want to compare is the tangent direction. So here's the tangent line, and I have parallel along it P prime of t. And I want to ask, how much does f disagree with P prime of t? So I have f at that point, and I'm going to draw it in a different color. So here's f at that point. And I want to know how much it disagrees. And so that disagreement should be the amount of f that is orthogonal to p prime. So put another way, what we could do is produce a vector that's normal to p prime of t, and we could ask ourselves, how much does f agree with n prime? So what I'm saying is that f orthogonal, if we ask for the orthogonal component of f, with respect to p prime, that's the same as asking for the parallel component of f along n prime. And so, in some sense, what this would be measuring is not how much of f is flowing along the curve, like on the left. So this integral was the flow of f along the boundary of r. Then over here, we're going to come up with another integral, which is the flow across. the boundary of R. And sometimes this flow across is abbreviated into flux. Flow across becomes like smushed together into flux of F over boundary R. So this is supposed to be the flow of F across the boundary of R. And what we need is an integral that we compute, dr, that adds up all of those little components. Well, so what we should do is we should take F, and we should dot it with not dp, which is p prime, but dn. And now I need to give a formula for n, and this will be our go-to formula. So if p of t is x of t, comma y of t, then n of t is always going to be y of t minus x of t. And what this does, oh, I am out of space. Let's just fit it onto the bottom of the page. I have my little, in case you wonder what these are, this is my little marker to make sure I don't write off of the page. So if you imagine the curve, here's our curve, and it's flowing this way, then at a given point you have its tangent line. Then if we're at this point, if this is p prime of t, which is the components of that are going to be x prime of t, comma y prime of t, then in order to get a normal vector, you should flip x prime and y prime and pick one of them to be negative, right? We are familiar with this from normal vectors. We're going to make it so that n prime is always outward facing. And so in order to do that, you make, if the boundary is oriented counterclockwise, then this choice of negatives makes it an outward-facing normal rather than an inward-facing normal, minus x prime of t. And then these are always orthogonal to each other. So this summarizes our new integral for flux. I also want to point out that this outward normal is a form of the right-hand rule. So if you treat the outward normal as your first part of the cross product and the tangent direction as the second part, you should be getting your thumb pointing off of this page, which follows the right-hand rule where you say that the plane is positively oriented if the vector coming vertically off of it is the orientation. So this is yet another case of right-hand rule in this class. And on the next page, we'll state Green's theorem with respect to flux. Okay, so the new Green's theorem with respect to flux is going to look like we are computing an integral, and instead of computing a flow integral, we're computing a flux integral. So this is Green's theorem. And people either call this the flux form or the divergence form. Your choice. I think most of the time I say flux form versus divergence form, but so over here we should be computing the flux, so dn. And on this side, we're going to get a double integral, because we tend to get that in these problems. So here is what our region looks like. Then the new flux form is we integrate over R the divergence of f dA. And so we need to tell you what, I need to tell you what the divergence is so that we can in fact compute this. And so we'll add a definition here. The divergence of f, and I should write this d with a lowercase d, that is standard, which is called the divergence of f, is also written as nabla dot f, and this is going to also tell us how to compute it, because if f, in our case, is m comma n, then nabla is d dx comma d dy, and taking a dot product is just taking a dot product. So I get dm dx plus dn dy. And that's all the divergences. So this is now a function of both x and y. So in this particular case, let's just write it out. So dm dx plus dn dy, all of that dA. And that's the divergence form of Green's theorem. Now, what does flow compute? What does flux compute? Flux computes the rate that f is crossing the boundary. And what does divergence compute? It computes how much f is expanding at a point. So let's give some heuristics. So divergence of f is how much f expands at a point, and curl of f is the local circulation or flow, let's say rotational flow, of f at a point. So the way you should think about what Green's theorem is doing is that we have these two different forms of Green's theorem. So on one hand, we have the flow form, which says that if you want to understand the flow around this curve, boundary of R, it's just adding up all of the different local flows inside of R. And the flux form says that if you want to know how f expands across the boundary, how much it's crossing the boundary, you need to add up how much is expanding kind of everywhere inside to know how much it has to be crossing the boundary. So let's kind of justify this. So imagine you've got this region, and I'm going to draw kind of the same region everywhere. And over here, on the left-hand side, we want to know how much f is flowing along the boundary. Now, if you could imagine dividing f up into lots of little subregions, where maybe each smaller region, f is doing, the flow of f is kind of constant. And after you do this, you could figure out, okay, maybe as you walk just around this one here, you can understand by adding up all of the local flows in this little region, you understand how much F is flowing around this boundary. But then to get it for around the whole boundary, maybe you also add them up for this boundary here. But when you do that, you realize, because you're always flowing counterclockwise, on this overlapped boundary, you were both going in this direction on the blue boundary and backwards it on the red boundary. And so those two cancel and essentially give you the flow along this much bigger region without that edge in the middle. And so as you keep expanding out, you can kind of cancel away your internal edges by adding on more and more flows around each of these regions. And so my green rotational arrows is supposed to be saying, if you zoom in enough where you can understand what the flow is going around the boundary because it's so constant everywhere, it's just a little spin that you can add up, then you could piece it back together into like big pieces using this type of gluing argument. This is the argument behind Green's theorem. For the flux form, what I'm going to try to imagine is, like, imagine you've got the sun in the center of this, and you're trying to measure how much light is crossing this boundary at a given second or something like this. How much luminance is going across this path. And so what you could do is you could break it up into little subregions again. And so let's do fewer. Let's go like this, like this, like this, and like this or something. And maybe you discover, oh, there's not only the sun, there's also a bunch of other kind of like shining lights in a couple of these other regions. And so you're trying to understand how much you get when you add up all of this light coming out of this region. Then you could figure out how much light is just coming from this innermost region. You could see like how much is shining out of that, and then compute how much of it has to shine across those boundaries. And then you check, and you're like, oh, and in this region over here, there's no lights, and so you figure out how much has to cross over these boundaries as a result of the light traveling and that sort of thing. And as you add these things up, the edges also cancel in the same way that they did to the left. So Green's theorem is all about kind of breaking down these regions into little sub-arguments that you can understand because they're locally constant. If this explanation did not make much sense to you, it's okay. It's really just supposed to motivate things. As we go forward, we're going to look at a couple of specific examples to try to understand what divergence is by looking at vector fields, and then we'll work a couple of examples with Green's theorem. So let's eyeball the flux of some vector fields just based on kind of quick sketches of them. So for this first example, so here's 1, here's 2, here's 3, and here's 4. So for the first example, you should imagine that you draw some curve, C, and you're asking about the flux across C, and it looks right now like the vector field over, as it crosses C is like almost entirely orthogonal to C pointing out. So you're gonna get positive flux. Because the vector field is flowing across C, outward. And so at any given little point, your normal direction to C and the vector field at that point are really close to agreeing with each other, and in particular their dot product will be positive, so you're adding up many, many positive dot products and getting a positive flux integral. So recall our integral that we're trying to compute is f dot dn for C. For number 2, if you draw a similar path for C, now your dot product should be negative because your normal direction is out. It's always the outward normal. If C is oriented counterclockwise. But your vectors at that point are pointing in, and so that dot product is going to be negative, quite negative, in fact. For number 3, imagine you've got some curve, and I'm going to make it more boxy here, because flux will depend on what the flux will depend on the curve that you're drawing, but the boxy ones are somewhat easy here. So when I look at this, my normal directions, I'm going to draw them in blue. They're all outward normals. Go that way. And on each of the sides, those directions are orthogonal to the flow of the vector field. And up at the top, I have, so I get nothing on either of the sides. So I get 0 flux on that side, none of it's going across, all of it's flowing down, 0 flux on that side. And on the top, I get a bunch of negative flux. So negative flux means it's flowing in to the region. But then on the bottom, I'm getting an equal but opposite amount of positive flux. And so since I have, which is flowing out. So equal amounts flowing in and equal amounts flowing out means that the flux should be 0. So total flux is 0 because they cancel. However, in example 4, you can see that even if I draw another box like that, let's just make it long to exaggerate it, counterclockwise orientation, right? Over here on the part where I'm flowing in, my vectors in my vector field are short, and over here where I'm flowing out, I have much longer vectors. So this is more flowing out than flowing in, so this has positive flux. So the flow out is bigger than the flow in, just by eyeballing it. Yeah, we will think more about this as we do more examples. So let's, as our first example, compute the flux of the rotational vector field over the unit circle, oriented counterclockwise. So because my unit circle C looks like this, and my rotational vector field, here's F, is completely tangent to this circle at all these points, my expectation is that the flux is 0. But let's compute that with parameters to make sure that we can make sense of these things and compute them, not just eyeball them. And that what I've told you about flux is in fact true. So, and I see I wrote dp, but I definitely want this to be dn for flux. So what we should do first is compute my parameterization of t, or of the unit circle. So I'll use our favorite one, cosine t sine t, for 0 between t and 2 pi. That means that my normal vector is going to be given, or n, whose derivative will be the normal vector, is going to be sine t minus cosine t. And then I can now compute my flux integral by passing to parameters. So I'm doing the integral of c of minus y, which is sine of t. Maybe I should write this out. Yeah, this is f of p of t dot, and then for dn, I need n prime of t dt. So this is maybe a little subtle, but you're plugging p in to f because I want f's value at p. So if this is my point p, I want f of p of t, if that's where I am at time t. Not f of n of t, which is just some other random point. So with that, let's point this out. And just to be really careful, once I've passed to t dt coordinates, this should be t from 0 to 2 pi. So that's more proper. Okay, so t 0 to 2 pi, f of p of t is minus sine of t cosine of t. That's f. N prime is derivative of sine is cosine of t. Derivative of minus cosine is plus sine of t dt. And now this dot product is minus sine t cosine t plus sine t cosine t dt. So my integral is just 0 because I'm adding up zeros everywhere. So my flux integral makes sense. It is in fact 0. Let's point out, though, that I could also have computed this flux integral using Green's theorem. So what if instead of computing it by parameterizing it, I tried to pass to a two-dimensional integral using Green's theorem? So let's do that. So if I use Green's theorem, this becomes a double integral over the unit disk of the divergence of this, so nabla dot minus yx, which is f, dA. And now nabla, this, let me scroll up a little bit more. So let's compute the divergence. The derivative of minus y with respect to x is 0, plus the derivative of x with respect to y is also 0. So, and just to be clear, this here is d dx of minus y, and this is d dy of x. And so, with Green's theorem, it also is very obvious that this is 0. So compare contrast with the radial vector field. So let's let f be x comma y. Basic example, C is still the unit circle. And now we expect to have flux because the radial vector field is crossing, so we expect in fact to have positive flux. Let's compute that. So the flux is going to be the integral over C of f dot dn If I want to do that through parameterization, remember P was cosine t, sine t. So N is sine t minus cosine of t. So my flux becomes the integral as t goes from 0 to 2 pi of cosine t sine t, that's f of p of t, dot cosine t sine t dt. And that means my flux is now cosine squared plus sine squared, which is 1, integrated from 0 to 2 pi dt, also known as 2 pi. Let's just also check that with Green's theorem. Check that this agrees. So by Green's theorem, this should be the double integral over the disk of the divergence. So taking the divergence of x comma y, which is not partial derivatives, it's taking certain partial derivatives and adding them together, right? dA. This looks like the double integral over the disk of 1 plus 1 dA. And to be clear, that is d dx of x plus d dy of y. Which means it's just 2 times the area of the unit disk. The area of the unit disk is pi 1 squared, which is also 2 pi. So one of the things that going back and forth between doing flux form integrals and flow form integrals does is it kind of switches the role between the radial vector field and the rotational vector field, because of how passing from p prime to using n prime swaps the coordinates and adds a negative in them, just like how passing from this radial vector field to minus yx swaps the coordinates and adds a negative between them. So it's kind of a matter of whether it's happening in the f part of the integral or in the derivative part of the integral, which side of the dot product that's happening on. Which is why, even though this flux form, and I think the book shows this, the flux form of the integral, you can always kind of reparameterize your function and turn it into a flow form of the integral. Which means that which means that both of these forms of Green's theorem are the same theorem, they're just kind of 2 different ways of thinking about the theorem. In fact, let's show that these things really are the same idea, that you can think of divergence as being a curl and vice versa. So the idea is that you switch what your vector field is. So taking a flux integral for mn dot dn over some curve c, then you know via Green's theorem that this is really the same as taking the integral, let's call c the boundary of r, of the divergence. Right? So this is the divergence of m comma n. Now, I can compute what that divergence is. The divergence is mx plus ny, right? And I wrote a dn, but this should be a dA. Here. And it just turns out that that's also the curl of a different vector field, the vector field minus n comma m. Right? So just to check, if you have the curl of minus n comma m, what that is you take mx minus ny, minus ny, which is in fact mx plus ny. So we've switched fields, right? On one hand, we had this m comma n vector field, but on the other hand, we can, over here, turn it into a minus nm vector field. All of these are still integrals over R. And then this is a curl of minus n comma m. So I can use Green's theorem again to turn that back into a flow vector field. And that vector field looks like C, which is the boundary of R, and it's the flow of minus n comma m along C. And this is a long string of equalities, so this means the flux of mn across C is the same as the flow of minus nm across C. So if I give an integral that just is a isn't written out as either a flux or a flow integral, but in terms of x's and dx's and dy's, you can solve it in either of these two ways. You could turn it into a Green's theorem one, or into a flux or a flow integral using kind of your choice of whether you saw it as being m comma n dot dn or minus n comma m dot dp. And this is really just your choice of two different ways. And so this is all just to say that both forms of Green's theorem are the same, and both are fundamental theorems of calculus, in the sense that they are taking something which is two-dimensional, this center integral, right? This could just be some function, dA, right? And either turning it into a flow integral that's 1 degree lower, so that's a one-dimensional integral of flow, or going left and turning it into a one-dimensional flux integral. So here's a harder f. Let f be 2x plus sine y, comma, xy. Let's compute the flux of f across the unit circle. The circle of radius 2. So I could choose to do this by parameterizing my circle. So I could let p of t equal 2 cosine t, 2 sine t, and then f dot dn looks like, what's n? N of t is 2 sine t, comma, minus 2 cosine t. So, and t here is 0 to 2 pi. Then my integral will become the integral from 0 to 2 pi of, this looks bad already, of 2 cosine t plus sine of 2 sine t, comma, 4 cosine t sine t, dot, and then all in there I need to put n prime of t dt. And as soon as you see this much parameterization, including that sine of 2 sine of t, which I'll underline, like that's just quite sad looking, right? Don't do this. This is bad. Instead, let's try to use Green's theorem because it's amazing, right? And so by Green's theorem, this should be equal to the double integral over the disk. This is the disk of radius 2 centered at the origin of the divergence of f dA. And the divergence of f is much simpler. In particular, that sine of y disappears. So it becomes the double integral over the disk, radius 2, of 2 plus y, 2 plus x dA. And now at this point, I would say maybe we could convert to polar notation, perhaps, to make this integral easier. So the disk of radius 2, r goes from 0 to 2, theta goes from 0 to 2 pi. 2 plus x becomes 2 plus cosine theta. 2 plus r cosine theta, sorry. And dA becomes r dr d theta. And now this integral doesn't look that bad. I've got, it's the r's and cosines, these has constant bounds, right? So this is not going to be that bad. So in particular, this is, if I rewrite this as this 2r plus r squared cosine theta dr d theta. So if I do the r's first, I'm going to get the integral theta goes from 0 to 2 pi of r squared plus a third r cubed cosine theta. R goes from 0 to 2 d theta. Which gives me 4 plus 8 thirds cosine theta, and at 0 everything disappears. Theta goes from 0 to 2 pi d theta. So I'm going to get a 4 theta plus 8 thirds sine theta, as theta goes from 0 to 2 pi. At 0 and 2 pi, sine is equal to 0. So I just have 4 times 2 pi minus 4 times 0, which is 8 pi, which is pretty nice. That's how much flux there is, 8 pi flux. So let's assume that f has constant divergence everywhere, which means that pretty much everywhere, f, depending on how big the area is, or put another way, in a unit area, f should have external flux 2, plus 2. Then we can use Green's theorem to get the flux across C2 from the flux across C1. One way to do this is that C2 minus C1 encompasses this whole inner region. So let's give a name to that region. Let's just call it R. So all of this region is R. So the boundary of R is C2 minus C1 if I orient counterclockwise. And so if I add up all the divergence over R, I know that that should be 2 times the area of R, which is 2 times 8, which is 16. This is times. But I also know that that should be equal to the integral over c2 minus c1, so that should be the integral over c2. Oop, and I wrote these as flux across integrals, but these are just, these aren't closed curves. So, sorry, they're flux integrals, but they're not closed curves, so I shouldn't get closed curves there. This should be the integral over c2 of f dot dn plus, minus the integral for c1 of f dot dn. And so this is what we want, minus 6 equals 16. So 16 plus 6 is 22. And that's our answer. For our fourth and final problem, let's consider D, the disk of radius 3, centered at the origin, and its boundary is oriented counterclockwise. We want to compute the integral over the boundary of this expression. What we need to do is unpack it into either a flux or a flow integral, and I'm going to do both. And our translation guide between them is, if we let P be x, y, then dP is dx, comma, dy. We've seen that in our line integral lecture. Then n, we said, is y, comma, minus x. So dn, n, is going to be dy, comma, minus dx. So if we want to get this as a flux integral, so let's label this integral I, and we can rewrite it in flux form. I is the integral which computes the flux of a vector field I'm going to call f dot dn, and dn is y, comma, minus, dy, comma, minus dx. And so what is the vector field f in this case? F has to be sine y squared plus 3x, comma, and then to get a negative on dx, I actually have to flip the order of the terms over here. So I get y minus cosine x squared dot dy, comma, minus dx. And so the negative is just going on the right part of the dot product rather than the left. And so critically, I'm using this vector field here for my flux integral. I can also compute this as a flow integral. Flow. And the flow integral, that looks more like the line integrals that we were used to before this lecture. It should look like, let's call it g dot dp. And so in order to get dp as dx, comma, dy, I just have to change my order of addition up here. So I get my vector field g is cosine x squared minus y, comma, sine y squared plus 3x. And that is dot dx dy. And so this starting integral that I wrote in black didn't tell us what the vector field is that we started with to get this integral. And what we see today is we have two dual ways of looking at it. It's either the vector field f or it's this other vector field g. And the question is just, are you thinking of it as a flux integral or as a flow integral? Let's just compute both of them with Green's theorem and we'll see where we go. So if we're doing this as a flux integral with Green's theorem, then by Green's theorem, my integral becomes the double integral over this disk of radius 3 of the divergence of f dA. And the divergence of f I can compute by taking partial derivatives and adding them. So the x component gets d dx, which is 3, and the y component gets d dy, which is 1, so 3 plus 1 dA, which is 4 times the area of the disk, which is 4 pi r squared. And that's my answer. For the flow integral, I also use Green's theorem to get the double integral over the disk of the curl of g dA. And the curl I also compute using partial derivatives, but you take the x derivative of the y component, so if you'll see, that's still this 3x, it's just in a different place now, so that's 3, and then it's minus the derivative of the yth derivative of the x component, which is minus 1. So that still gives me 4 times pi 3 squared. I think that's a good place to stop for today. I hope everyone has a good weekend. I do want to remind you, so the curl we wrote as nabla cross G, and we justified that last time, or Monday's class. And the divergence we're writing as nabla dot F. And both of those are going to be the way that we generalize curl and divergence in 3 dimensions. So on Monday, we're going to start working really rigorously in 3 dimensions. I want everyone to be ready to rock and roll with those new definitions. So we'll be seeing this stuff come back Monday and Wednesday of next week, and also just all the rest of the semester. Have a good weekend. Stay safe. Stay healthy.